Okay, so we'll continue with this data flow modeling as a part 2, which is continuation from lab 3, where we were taught the initial version of the data flow modeling and some initial assumption and what is that, what do you mean by data flow modeling, so on and so forth. This session will learn into more detail about the data flow modeling, and by the detail means I mean just one statement, continuous assignment. That is the backbone of the whole modeling technique of the data flow modeling. What it basically do is an assignment statement of A equals B and C bar, for example. It means that, like, whenever the value of B and C changes, go and evaluate value A. So it is a continuous, always active assignment between the variables. The equivalent of the behavioral modeling would be like always at B or C, B in A, B and A equal B and C bar, and so it says that always if B or C changes, go and evaluate A. Instead of typing all these things, we can just do this little thing here, assign A equal B and C bar, which is equivalent and which is actually saves us from typing much more things as in the behavioral modeling. There is an assumption between the what can go in the left hand side versus right hand side. Left hand side must be a net. It can be a scalar net, it can be a vector net, it can be a concatenation of scalar or vector net. Doesn't matter, but it cannot be a register. It has to be a net. On the other hand, a right hand side of the equation can be a register or net or a vector of register or net and something like that. It can be anything practically. So this is a little rule we need to keep in mind. And going forward, let's do some example assignment, like a net to net assignment would be, okay, let's say these are the input nets I1, I2, and we're continuously assigning out equals I1 and I2. And register vectors assignment like these are like an address of 16-bit. We're doing an XOR between address 1 16-bit and address 2 16-bit, between that and assigning the XORed value, the evaluated value of these two, into the address. Concatenation, we'll see that concatenation operation, but practically this is the curly braces open and close, and then we do a comma separated list. So this means the eventually the whole right hand side will be assigned into the left hand side, which is 4 plus 1, in this example 5-bit long. Okay, so there is a 4-bit A, maybe register or net, 4-bit B, and a carry in operation. We'll see the carry in carry out in our when we study the addition operation, but it's just that the same concept. It's a 4-bit, two 4-bit variable we're adding up with an carry in, and whatever is coming out we're assigning to a 5-bit quantity, which is composed of a cout as a most significant bit, and the sum, which is a vector net of 4-bit. Now there is an implicit continuous assignment which saves some more typing, like we do an where out, which is assigning this a net, and then we do assign out I1 and I2. Instead of doing that, we can do where out equals I1 and I2, which is same. So we are saving some typing here, but no, by not typing the assign statement explicitly. Now we review some of the operators we do in the assignment statement. Is similar to what we have in C and Java. Most of them, like addition, subtraction, multiplication, division, modulus, logical not, logical and, logical or. We have like greater than, less than, greater than equal, less than equals. Equality operator, let's look into a little more detail. It's a little bit different. We used to have in C or Java as a equal equal, which is like equality between two variables. But remember, in the Verilog we deal with the value x and z along with 0 and 1, so we have 4 different values. This equality operation doesn't actually handle the value x and z, which means, let's say we have two variables, a equal b, and a value is x10 and b is x10. We normally think, okay, they are equal because it is both of them are x10, but equal doesn't handle x, so it will return false practically. Okay, similar with the, if anything involved with the z, like 1 z 0, if both of them right hand side left hand side are 1 z 0, still will get a false equivalency there. And not equals is just inverse of equals. Now to get rid of this problem, Verilog introduced this triple equal convention, equal, which actually takes care of the case equality. That means if we do an a equal b, where a value is again x10, b is also x10, it will actually return 1 in this case, unlike the 0 for the equal, because then it matches this x to x, so both of them x, okay, they are equivalent in this operation. Okay, so we usually use this triple equal very often instead of double equal, because we are more interested in the bitwise comparison with handling x and z. Okay, and not equal just the inverse of equal. Now we have bitwise operation, like you have probably familiar with this with the project one, like negation, and, or, XOR, NOR, XNOR. And we have one special operation called reduction operation. Like, let's say if I do a variable and x, what does it mean? That will return a single bit value, 0 or 1, or z or x, depending on what the value of the x variable is. But let's say this x is a 4-bit, which is 0 1 1. So and x means we are doing AND operation between these bits. Okay, so 0 and 1 and 1 and 1, which will result in, of course, 0 as a bit. Now this is NAND of x, or the same value, of course, evaluated to be 1. Similarly for the OR, it will be OR between all these bits, 0 or 1 or 1 or 1. Of course, it will evaluate to 1 in this case, and NOR, X or XNOR. There are some other special operator like left shift, right shift, same as a C and Java. This is a concatenation. It practically says that I'm grouping different nets or registers together, like cout. This is a 2-bit 0 1 2 3-bit register, something like that. So it becomes total of 4-bit value concatenated together, which is assigned to the out, which is 4 bits. So this is a concatenation. We can put list and group them together and assign into a bus or something like that. Now replication is a tricky operation. It's basically replicates one given value. Okay, so let's say there is a 1-bit variable a, b, and c with this 1 0 and 1 value, and then we're assigning like a 7-bit net y with this like 4 of A, 2 of B, and C, which means A will be 4 of them replicated like 4-bit place. Like this A is 1 bit originally, but 4A, like this operation, replication operation, it will equivalent to saying that A comma A comma A comma A. Okay, so instead of doing a 4A comma separated, we are just saving our typing by 4A, which is like replicate A into 4-bit place and replicate B into 4-bit place. So as a result of this assignment, the value of Y will become 1 1 1 1. This 4 1 comes from replication of the bit value A 4 times 1, and 0 0, which will be replication of bit value of B, which is 0 for 2 times, and C comes directly here. So that's the one. And of course we have the conditional assignment like C or Java, which is A equal, for example, A equals B less than C, query B or C, which means if B less than C, if this is true, then assign B to A, else assign C to A. Okay, so I think this is all we need to know about the data flow modeling. It's a backbone statement, it's the assignment statement. With different of this operation and combination, we model data flow between different elements in the Verilog, different registers and operations and nets and their relationship. And in fact, in reality, we actually model, like, we don't purely model in data flow, we don't purely model in behavior. We kind of tend to mix each other as we need to model some whatever we want to model, like a processor or a memory or something like that. So that's all from the slide perspective, and next we'll show you a demo of this lab 4, which is an ALU. We as in the project 1 we represented ALU in a Weber model. Now this lab will represent in a data flow modeling way, and I will explain the statement and so that it makes sense to all of you. So we'll start the model sim soon, and we see that whole process. So for that demo of the ALU example of the ALU modeling with the data flow modeling, what we need to do first, download from the canvas the alu.v file. I have uploaded that this alu.v, just download and store it into a directory, and it's basically let's say we store it alu.v, and then copy the project 1 test bench and project definition from our project 1 directory. So for this, and now we will start the model sim, create a project around it, and we'll demo what it is. Okay, so we open that, and let's say we want to create a new project. Okay, and let's see, this one is left for demo. Okay, and project name, let's say give ALU data flow. Okay, so now I add existing file, browse, I'll add all these 3 ALUV, this one, close. Now let's open the files, like alu.v will look like this. This is very short, compact kind of coding implementation, and project TB is basically the same one, right? We just borrow it from the project 1, and we have test and all this stuff. So let's go and compile it. Of course, definitely the project definition is the same as the project 1. So we are more interested in this modeling on the data flow modeling of the ALU. So we compile all, and then we run the TB test bench. Okay, so let's see. Okay, so what I want is to add operation OP and the test to add them, these 3 operand 1, 2 and operation value, and also the result net. Right click into add to wave. So I believe wave will have that. Okay, so I will also just put them a base, all of them radix to, let's say, decimal, and we run it. So So we run all. So after some time it will hit this $stop, which will stop the simulation. And let's look at the transcript where we got testing all test passed, like 15 plus 5 is 20, 10, 5 into 5 is 75, so on and so forth. So basically all of the test pass as we did on the project 1. So the modeling perspective, though ALU is a different written in a data flow model, it still do the same thing. We can also see the waveform here, right? Okay, so we have 15 plus operation, which is 20, and this is minus operation, which gives 10, and this is 3, which is multiplication, gives 75, this is division, gives 3, so on and so forth. So seems like it's working fine. Now look at the file itself. So its port definition is the same as the project 1 behavioral model. It is the same as result, OP1, OP2, OPRN. There's input, 32-bit input, OP1, OP2, 4-bit I think operation code, and then output is of course 32-bit, so result become like that. Now look at this assignment statement. So we, in one single assignment statement, the result to continuous operation, continuous assignment was assigned to, like let's say we are checking with a triple equal. Okay, note the triple equal here. Operation if equals to 1, code 1, which is add. If it is true, then assign result as OP1 plus OP2. So addition. Else the whole thing. So you need to be very careful about this parenthesis with this modeling. This can be like, can results into really cryptic error message. Okay, so you better write in very systematic way, right? Else everything is under one whole bracket. Okay, this versus this. So you write that first, and then so else if the operation is subtraction, do OP assign result as OP1 minus OP2, else another whole bracket. Okay, see the opening and closing braces, you need to keep track of that. Okay, so it's basically if this, else that, and so on and so forth. But if else, those things are behavioral model, or switch case statement is in behavioral modeling. For the data flow modeling, all we have is this query and colon operation, which gives, okay, test something. If it is true, assign some value to the left hand side, else you do everything. But we can actually go on like this with different cases. We can compare and do the assignment, and ultimately at end, if it doesn't match anything, then you would put x there. So this is the data flow modeling we use. As I mentioned earlier, that we don't use a pure data flow modeling and pure behavioral modeling. In a sense, we kind of mix and match as needed, whatever way it's easier for us to implement. For example, if I have given choice to implement ALU and behavioral versus this data flow modeling, I'll go for the behavioral modeling because that's easier to write, and it's easier to kind of go and understand what's going on with the case statement, and it is not that much prone for syntax error like this one. This becomes really complex and cryptic, long lines. Okay, so that's all we want to show as a demo on the data flow modeling of the ALU. So it functions same. We have the same test bench, ran around, plugged in this model, got the same result as the transcript says, all test pass, so we are good to go. So I think that's all of that demo. I hope you will do this experiment yourself and go and read and try to understand all these things, all the modeling aspect of this data flow modeling as exemplified in this ALU model. So good luck with your